This is the University of Hawaii Maui College, the college on Maui.
Today we begin basic pharmacology principles. And you'll notice as this lecture goes along, the reason I give you the yellow print is so that you guys think that I'm giving you test questions, and you've noticed that that's pretty much true. And for this lecture, we can just assume that the entire lecture is in yellow print, and most lectures I give after that. Well, this is a pharmacology class. It would be nice to know the actual definition of pharmacology, and that's this right here. Pharmacology is the study of substances that interact with living systems through chemical processes, especially by binding to regulatory molecules and either activating or inhibiting normal body processes. Yeah, it's a big set of words, but I'd like you to give some thought to it, because pharmacology is about manipulating already existing regulatory systems in the body and trying to get them to do things that help. In this course, pharmacology is not the memorization of long lists of medications or any of the drug companies' latest products. Some people think that I stay real current with all the brand new things that the drug companies are coming out with, and the only problem with that is many times a lot of the things, the brand new things drug companies come out with are things that the drug companies end up taking off the market. And so I try to spend time on tried and true old classes of drugs and let you see what the similarities are among them. But what this course does intend to teach you is how medications are used to treat and prevent illness. But what I really want to get across to you this semester is to reveal to you the complexity of living regulatory systems, especially human beings. So this course is going to get enormously complex because of all of you are enormously complex. And so keep in mind that is your fault, not mine. Well, medical pharmacology is the science of substances used to prevent, diagnose, and treat disease. And that seems to make some sense. Toxicology, as in toxic, toxicology is the branch of pharmacology that studies the harmful effects of chemicals on living systems. And a drug, we hear drug used all the time on TV and pop culture. I want you to keep in mind that our definition of a drug is just a little bit different. A drug is any substance that interacts with a molecule or protein that plays a regulatory role in living systems. And so that makes the definition of drug much larger than how it's used out there in TV land. And we're going to come back to this point later next week. Here's a word they throw around all the time like you know what it means: endogenous, endo, meaning inside. Genus, as in Genesis, means the beginning or how it's made. So endogenous substances are made inside of the body. And all of this is written down for you in your notes in the resources section, so please don't get carpal tunnel with all that scribbling. Exogenous, on the other hand, exo, outside, genesis, as in the beginning. Exogenous substances are made outside of the body. Well, hormones are a word that I hear used in all sorts of contexts, but in pharmacology class, hormones means something different. Hormones are just quite simply endogenous drugs. Hormones are drugs made by the body. Well, I never used this word. This word never came out of my mouth until I read Katsung and started teaching this class. Xenobiotics, xeno meaning different than a human being. Xenobiotics are exogenous drugs. Now, one thing, if you have Katsung's Basic and Clinical Pharmacology or any book written by multiple authors, you'll notice that the authors that write one chapter do not completely agree with the authors that write another chapter. And if you pore over Katzung's clinical pharmacology book very, very carefully, which I'm sure you all do, you might notice slight variations in this definition. But for the purposes of passing this class, xenobiotics are exogenous drugs. Poisons are drugs too, but poisons have almost exclusively harmful effects. Now, plenty of people who teach pharmacology will tell you that all drugs are poisons, but that really just depends on the dose. You can kill anybody with anything based on that definition, and so our definition of poisons is this right here. Poisons are drugs that have almost exclusively harmful effects. Toxins, we hear about toxins all the time and how to get the toxins out of us, but here in this class, toxins are poisons of biologic origin. That means toxins are naturally occurring, all natural poisons, and they are usually synthesized by plants or animals. Well, this is important. We'll use the word receptor all the time in pharmacology. And we can think of receptor as a lock that a key goes into. And so a receptor is a specific molecule, usually a protein, that interacts with a specific chemical, like a key, and then causes a change in the specific molecule, causing a change in the regulatory function. So I want you to spend a little bit of time thinking about keys and locks. If you take a key and you can stick it in the car door and make the car door open. And so we can think of the key as a drug and the lock as a receptor. Well, this word looks like agony for a very simple reason. We'll use the word agonist all the time in this class. An agonist is any drug that binds to a receptor and activates the receptor. And so here is my phospholipid bilayer that I drew for you at the second lecture. This is a protein receptor, kind of like a lock. And here is a place for the little key to go. And if that key activates this receptor, then it's an agonist and will cause some kind of change in that receptor. Remember, the top of my slides are always the outside of the cell, and underneath the phospholipid bilayer is the intracellular part of my cell. And so here is an agonist that comes in contact with the receptor, and notice it activates the receptor, and the receptor is able to cause some kind of chemical reaction inside of the cell. This is a natural occurring process of the body and how it regulates itself. And so if the agonist comes from inside of the body, if the agonist is made by the body, well, then that agonist would be referred to as a hormone. If that agonist was made outside of the body, we can refer to it as either a drug, preferably. We don't use the word xenobiotic too much in clinical medicine. Actually, not at all. An agonist is any chemical that activates the receptor. Any drug that activates the receptor would be a good way to describe that. Well, I throw this in many cases, when the agonist leaves the binding site, it just deactivates the receptor, and this is what occurs normally, at least in my cartoon series. However, other receptor agonists will permanently activate the receptor. Saw this as a board question. It's kind of a curveball. And so I did want you to know that there are situations where the agonist will make a covalent change to the protein receptor, so that when the agonist leaves the receptor is permanently activated and will remain permanently activated until that receptor is broken down naturally by the body. Well, that brings us to pharmacologic antagonist. A pharmacologic antagonist is any drug that's going to bind to the receptor and prevent the activation of the receptor. And we talk about antagonists all the time in pharmacology. So here again is a receptor, and it comes in contact with an antagonist. And notice the antagonist does not activate the receptor. The agonist is what activates the receptor. So here, because this chemical fits into the lock but does not activate it, then we refer to that as an antagonist. And in this cartoon, this is a competitive antagonist because the antagonist is competing with the agonist at the agonist's binding site. So notice that the agonist cannot activate the receptor in the presence of a competitive antagonist. So there's our definition of competitive antagonist. A competitive antagonist is any pharmacologic antagonist that competes with the binding of agonist at the binding site. Well, that brings us to non-competitive antagonists. And non-competitive antagonists are very commonly used in pharmacology, and so you'll see this term used a lot. Non-competitive antagonist is any antagonist that binds to the site on the receptor other than the agonist's binding site. And so let's see if we have a cartoon of that. Here is a non-competitive antagonist. And notice it has a place somewhere else on the receptor so that it can modulate the function of the receptor. And this is very common in pharmacologic systems, biologic systems. So here's the non-competitive antagonist. Notice it's bound someplace else besides where the agonist will bind. So notice that if the agonist comes along and fits into the receptor, the agonist can't activate the receptor, or at least can't fully activate the receptor because of the non-competitive antagonist. Well, that's all different than a chemical antagonist. A chemical antagonist is any drug that binds directly to an agonist and deactivates the agonist. Well, so here is a chemical antagonist. There it is, right there. Notice it's not going to bind to the receptor. It's going to bind to the agonist and deactivate the agonist. Now the chemical antagonist prevents the agonist from binding to the receptor. Heparin is something that we'll use. We'll call that a blood thinner for now. And protamine is the chemical antagonist of heparin. And I can assure you that they will ask you that on some question, especially in this class, because that's a very typical example of a chemical antagonist. There's another thing called a physiologic antagonist, and I think I explained that in the next lecture. That slide is missing from here. A physiologic antagonist is like histamine and epinephrine. The end result of those two drugs or hormones are exactly opposite of each other, but it's through completely different physiologic pathways, completely different receptors. And so you'll read about physiologic antagonist, and I'm sure that's in my next slide presentation. Well, just like locks and keys, if you think about a key as being a drug and a lock as being a receptor, then you know that keys, just like drugs, must have specificity. A key must have a specific size, a specific shape, a specific cut to interact with a receptor. And so whether it is an agonist or an antagonist, all drugs must be specific in size, in the ionic charge, in their molecular shape. They have to be a specific size, charge, and shape to interact with a given receptor. Well, my predecessor used to say, a drug's got to get there to work. And so a drug must be able to be absorbed. If you take a drug by mouth and it passes through you and passes out of you completely unabsorbed, well, the drug's not going to do anything. So part of pharmacology is understanding that drugs must be absorbed by the body. Drugs must have delivery. A drug must be able to get there to work. And so a drug must be able to be delivered to the site of action. And so you can think about taking a pill and it going to your stomach and through your small intestines and the drug passing through the gut wall into the portal blood supply through the liver and then into systemic blood to be delivered to all the parts of the body. And so a drug must be able to be delivered to the site of action. And eventually, the drug needs to be eliminated from the body. Drugs can't stick around forever. Drugs must be eliminated at a reasonable rate. Well, most drugs are weak acids or weak bases. And so let's talk a little bit about why. So we'll talk about weak versus strong acids, weak versus strong bases, weak versus strong anything. And so this is my picture of a beaker of water. Water is a polar solvent. Solvent meaning it dissolves things. Polar, I explained in the last lecture. And so water is a polar solvent. And let's just take sodium chloride, which is just table salt. It's a white powder. And so let's take this sodium chloride and throw it into the water. You can do this at home as your own experiment if you would like to. And so we take this white powder, sodium chloride, and if we toss it into the water, it gets dissolved, and it seems to have disappeared, and I'm sure we all know better. And so we can take the sodium chloride, and when we toss it into the water, what happens? Well, it's dissolved, and it is divided into sodium ions and chloride ions completely. The white powder completely dissolves into sodium and chloride ions. So strong just means complete association. When we threw the sodium chloride white powder into the water, this arrow points to the right, meaning the equation is moving towards the right. The sodium chloride completely becomes sodium ions and chloride ions. Sodium chloride completely dissociates into its ions, and that just means strong. So let's talk about a strong acid. Here again is my water, my beaker of water, and we'll take hydrogen chloride, which is a white powder, at least on this cartoon, and we can take that hydrogen chloride and just toss it in the water and see what happens. And when we toss hydrogen chloride into the water, it completely dissolves into hydrogen ions, which is the same thing as a proton, which is the same thing as acid. It divides into hydrogen ions and chloride ions completely. So strong means complete dissociation, not how much it burns. Hydrogen chloride completely dissociates into hydrogen ions and chloride ions. That makes hydrogen chloride a strong acid. And I think I made that clear. Same thing for a strong base. Sodium hydroxide is a white powder, at least on this cartoon, and we can take the sodium hydroxide, toss it into the water, and it will completely dissolve into sodium ions and hydroxide ions. And that hydroxide ion we'll refer to as the base of this liquid. And so here, this strong base means complete dissociation. The sodium hydroxide completely dissociates into sodium and hydroxide ions. So we have completely described strong and strong acids and strong bases. So we have a beaker full of sodium ions and hydroxide ions. By the way, if we take our proton and mix it with a hydroxide ion, we'll end up with water, which neutralizes the acid and the base. The acid and the base neutralize each other. Adding bases to acids, acids to bases neutralizes them. Just wanted to throw that in. All right, now remember, while you were awake last time, most drugs are weak acids or weak bases, and this is actually very important in pharmacology. And so weak just means incomplete dissociation in water. Most drugs are weak acids or weak bases because they do not completely dissociate in water. They only partially dissociate in water. But we have a cartoon of that. We'll take our weak acid. Aspirin's a weak acid. It is all this chemical business with a carboxylic acid group, and aspirin is a white powder. We'll take all that chemical group and call that just R, which is a variable group in any description. And so R is just any chemical. In this case, it's aspirin. And here is our carboxylic acid group. And so we'll take this aspirin and toss it into the water. And what happens? It does not completely dissolve. Some of the aspirin is still in its powder form. Some of the aspirin is still in its ionic form. Why are most drugs weak acids and weak bases, or weak bases? And that's because of this right here, because now we have a balance between the uncharged aspirin and the ionic form of the aspirin. That means this form of the aspirin with no charge is lipophilic or fat soluble. And notice it's partially balanced with the ionic form of the aspirin or the drug. And the ionic form is going to be hydrophilic or water soluble. So most drugs are weak acids or weak bases, so that there is a balance between the fat soluble and the water soluble form. So let's go back to table salt and talk about something called mass action. It would be easier to call this saturation, but it gets too complicated for that. So let's talk about saturating the water with sodium chloride and what mass action means with that. So here's our sodium chloride. When we threw it in the water, it completely dissociated, but if we keep throwing the salt into the water, there comes a point where the water is completely saturated with sodium and chloride ions, and we get to the point where the water just won't accept any more table salt. It's saturated, and any more table salt we add after that will not dissociate in the water because it's saturated. And so instead of dissolving, mass action of all those sodium and chloride ions, because the beaker is just full of sodium and chloride ions, they start forcing the equation in the left-handed direction, meaning those sodium chloride ions are pushing back against the table salt and saying, hey, we're full, we don't have room for you, you just stay a white solid in the water. And so that's how we use the word mass action to describe saturated. So before it gets any more complicated, I want to make sure you understand what pH is. pH can be a measure of acidity, and if something has a pH of less than 7, it's acidic. pH is also a measure of alkalinity, which is greater than 7. When I write test questions, I always put the best answer first, even when the answer is all of the above. And those of you having problems with the quiz, I can assure you that is their problem. And one of my favorite questions is this one right here. pH is a measure of acidity. And they will check A as the correct answer and move along and not notice that pH is also a measure of alkalinity. And so both of the above would be correct in this case. And so if we have a solution with a pH of 7, that means there's an excess of hydrogen ions dissolved in the solution, because hydrogen ions define the acidity of the solution. And so this mass action of the hydrogen ions can push the equation towards what's called the protonated form of the drug that has that proton on it that will be released into the water. So here is some acid. It could be aspirin. It could be any chemical with this carboxylic acid on it. And when we toss it into the water, remember, it balances almost between its uncharged form, which is fat-soluble, and its ionic form, which is water-soluble. And so see, here is the protonated form of the drug, and it dissolves in the water and releases the proton right there, making it an acid. Well, if I make the solution acidic, meaning less than 7, that means there are an excessive amount of protons or ionic hydrogens in the water. And if I throw the aspirin in there, notice that the protons that are in the water push the direction towards the protonated form of the drug. Those hydrogen ions that are already in the water saying, hey, we're full. We don't need any more of that. So they push the equation that way due to mass action. Well, alkalinity, at least in this class, is a pH of greater than 7. Alkalinity means the solution is able to remove any excessive protons from the solution. And so this mass action will pull the equation towards the unprotonated form of the drug. So notice, if I take my aspirin and throw it into an alkaline solution, which means it has the ability to absorb those protons, notice that we can make the drug essentially completely dissolve because the mass action of hydrogen is being pushed in that direction. And so notice that, again, these bases that we've placed in the water and made the pH greater than 7 are able to pull the protons or the acids off the drug and pull it completely towards the ionic form of the drug. So what does all of that mean? Well, people ask board questions about this right here as if you know everything about it. So we at least want to talk a little bit about this term and what that means in pharmacology. The pKa is the pH at which the molecule or drug is completely balanced between the uncharged form, which is fat-soluble or lipid-soluble, and the charged form, which is water-soluble. So again, the pKa is the pH, the measure of acidity or the measure of alkalinity, the pH at which the molecule or drug is completely balanced between both forms. So most drugs are weak acids or weak bases for this right here, because only small changes in pH are required to shift them between their lipid-soluble form, which easily passes through cell membranes, and the water-soluble form, which does not. Now that makes sense because our stomach has an acidic environment, and so most drugs are weak acids or weak bases. We can put them in our stomach, and that pH of 3 or so, because of the hydrochloric acid in our stomach, can push the drug into its fat-soluble form so that it can pass through the cell membranes. And once it passes through the cell membrane and enters a place where the pH changes, that drug can shift into its water-soluble form so it can be delivered around the body. And so this is an important concept in pharmacology. Most drugs are weak acids or weak bases because only small changes in the pH can shift them between their lipid-soluble and their water-soluble forms. In the case of tricyclic antidepressant overdose, we'll alkalinize the blood with sodium bicarbonate, and this changes the effect of the drug on the body. So by changing the pH of the body, we can protect the person from the toxicity of tricyclic antidepressants for the reasons I just got through explaining. Well, for those of you doing the calculus and keeping score, that is all based on this equation right here, the Henderson-Hasselbalch equation. And that quite simply means the logarithm, I think I explain logarithms later, of this fraction right here. R meaning any chemical, and its protonated form, the concentration of that divided by the same drug in its unprotonated form. And so if you take the log of a drug in its protonated form over its unprotonated form, that should equal the pKa of the drug minus the pH of the solution. And I will let you find the solution on how to prove the pKa based on this right here, Henderson-Hasselbalch. But for the rest of us, as long as you remember that physiologic pH is about 7.35, which is slightly on the alkaline side, I'm sure you will do just fine in here. You don't have to worry about doing all the math involved with that. I just wanted you to see it. All right, so drugs interact with receptors by means of chemical forces or bonds. When a key goes into a lock, those are completely physical forces. When drugs interact with receptors, it does so with chemical forces or bonds, which is why we spent all that time with all that chemistry business last week. So affinity means how tightly the receptor binds to the drug, or how tightly the drug binds to the receptor. Now this is an important concept. When you take your key and you put it in the car door, you don't want that key to stick to the car door really, really tight. You don't want it to be hard to pull out. You want it to be very easy to put in and easy to pull out. Same thing when the key is in the ignition. You don't want it to be real hard to pull out. On the other hand, you don't want it to fall out while you're driving around. So how tightly the key binds to the lock is actually very important in the function of the lock. And that works the same way for drugs. How tightly the receptor binds to the drug is called affinity. All right, so here are drug-receptor interactions. Drugs interact with receptors by means of chemical forces or bonds, covalent bonds, electrostatic bonds, lipophilic bonds. And down here in very fine print, because I don't talk about them too much, are the van der Waals forces. If you see van der Waals forces, be sure and include that. Those are subatomic forces that you can read all about if you read about any book from Stephen Hawking. But most of what we talk about is covalent, electrostatic, and lipophilic bonds. So covalent bonds, meaning sharing electrons. We talked about covalent bonds in chemistry part of this. Covalent bonds are very strong and are usually irreversible. So when a drug makes a covalent change on a receptor, that's usually irreversible. Take the case of aspirin. You see on TV they tell you to take aspirin to prevent heart attacks. It's actually very good at that. Actually, somebody coming to the emergency room that's thought to have a heart attack, the first thing they want to do is give them an aspirin. Well, I'm here to tell you that aspirin floats in your body for just a little bit and then just passes right out. And yet the aspirin causes a covalent change on the platelets that lasts forever, or at least for the life of the platelet, which is about 3 months or so. And so covalent bonds are very strong and are usually irreversible. Drugs also interact with receptor by means of chemical forces or bonds like electrostatic bonds. These are pretty strong. Ionic groups, positive charges and negative charges, are going to be attracted to each other. I also talked about hydrogen bonding, where the hydrogen of one molecule would be attracted to the nitrogen or the oxygen of another molecule. And so ionic bonding and hydrogen bonding are essential drug receptor interactions as well. But this is also very important right here. The hydrophobic, meaning water-hating, same thing as lipophilic. It's the same thing in this class. Lipophilic, fat-loving. And these are weak bonds, but these are very essential bonds in drug receptor interactions. And if you read very modern pharmacology textbooks, you will see that these bonds are much more important than we realized in the past. And this just kind of sounds boring. That's why it was never really in the spotlight. And of course, there's van der Waals forces. I don't really talk about subatomic forces too much unless I was teaching a class on theoretical physics. And there's our van der Waals forces, and they're very, very, very weak. Now we've described them. Okay, so here is a term that's interchanged with its partner constantly. Please do not correct other people by what you've learned in this class. Don't ever tell anybody, oh, well, Dr. Farmer said this in pharmacology class. Just know that I'm telling you these secrets so that you can be successful in your careers and, more importantly, pass tests and pass boards. So pharmacodynamics, dynamics is the actions of a drug on the body. That's different than pharmacokinetics, the actions of the body on a drug. And so these are two very important terms that I want you to be able to distinguish. Dynamics is the actions of the drug on the body. Kinetics is the action of the body on the drug. And so here's an example. Pharmacodynamics, the action of drug on the body. Now, first of all, exam 1 does not talk about specific names of drugs. All right? Exam 1 is all about concepts. Specific names of drugs, we will throw plenty of that at you for the remainder of the semester. But here's an example of a drug, propranolol. It's a beta blocker. And in pharmacology class, we refer to beta blockers as beta adrenergic antagonists. And this means that it lowers blood pressure and heart rate. That's the action of the drug on the body. It's a beta blocker. It's a beta adrenergic antagonist. It antagonizes beta receptors, preventing agonists from activating them. And this lowers blood pressure and lowers heart rate. That's the action of the drug on the body. But pharmacokinetics is the action of the body on the drug. Propranolol is metabolized and eliminated by the liver and the kidneys. That would be a description of pharmacokinetics, what the body does to the drug. And so if you can remember the difference between these two terms, then you will cut the amount of time that it takes you to research drug information in half. As long as you know that you're looking for what the body is doing to the drug, then you can look in the kinetics section. If you want to know what the drug does to the body, then you look in the dynamics section. So the terms pharmacodynamics and pharmacokinetics are commonly, if very commonly, interchanged among all sorts of medical personnel. People come up to me and talk about the pharmacokinetics when they think they're talking about pharmacodynamics and vice versa, and I just let them because I know what they're talking about. I'm not going to correct them, neither should you. And so don't be surprised if you see the words dynamics and kinetics interchanged amongst the medical personnel. However, for this class and your boards, you will be expected to know the difference. All right, well, drug receptors are responsible for the selectivity of drug action. And that makes sense. Think about your car key and your car. You can take your key and if you stick it in the lock of the door, then it will open and unlock the door. If you take the very same key and put it in the ignition, it won't open the door. It'll start the car. If you take the very same key and put it in the glove box, it won't open the door or start the car. The key will open the glove box. The same thing goes for putting the key in the trunk. And so it's the locks that are responsible for what the key does, not the key. And this is the concept we're trying to say here. It is the receptors that decide what drugs do, just like it's the lock that decides what the key does. And that's the statement. That's the concept we're trying to get across with this statement. I want to talk a little bit about natural curves. Natural curves occur in the universe for very natural reasons, and they are all related to the same thing. And so the interaction between a drug or ligand is just a very fancy way of saying drug or chemical. And so the interaction between a drug and its receptor can be described by a curve. So because drug affects natural regulatory processes, it makes sense that their effect will follow a natural curve. So let's talk about concentration and response. Let's take ibuprofen, for instance. Ibuprofen, Advil, Nuprin, little yellow, just the same. And so if you take one Advil, you'll get a pretty good response. If you take two, you might get a better response. If you take 3, which is not recommended by the label, you might get a little more effect. If you take 4, you might get just a little bit more effect after that. And then taking 5 or 6 or 7 Advils, all you're going to do is get toxicity from that. You will not get more effect. So you can think about that as we talk about the natural curve. So the response to a drug is usually going to increase in proportion to the dose. As the dose gets bigger, the response is going to not be so much. We have a cartoon for all this. And at some dose, there's going to be no further response to the drug. And so we will describe this using Cartesian coordinates. So this is the agonist concentration, and this is the agonist effect, and we're getting ready to describe the agonist dose response curve. And so this is 0. As we go out here on the axis, the agonist concentration will be greater, and as we go up on this curve, the effect of the drug will be greater. And so this is our agonist dose response curve. Notice when we add a little bit of agonist, we get a pretty good effect. So our response is increasing in proportion to dose. There it is, a little bit of dose, a little bit of effect. Notice we add a little more drug, we get a little bit more effect, but not as much. Response still increasing in proportion to the dose. We add a little bit more drug, and now we have half of the maximal effect. The maximal effect would be all the way up here at the top, and notice that we are halfway to the maximal effect of the drug. And so notice how small a concentration on this curve is required to get to half of the maximum effect. And so that half of maximum effect, we call that the EC50 when it's concentration, or ED50 if they're talking about dose. The curve looks the same. So now we've defined the concept of EC50 on this curve. So notice only a small amount of drug is required to get half the maximal effect. Notice from here on it's going to take more and more drug to get all the way to maximal effect. And eventually we can add drug all day long and we will not get any more effect. And by the way, this curve, as it goes up and almost reaches that natural line and goes on and on and on forever that way, that is the definition of asymptotic for those of you who asked. So notice from here on out we're not going to get any more effect by adding more agonist. Not much, all right? Notice we can add a lot more drug and only get a little bit more effect. And we can add even a lot more drug and only get a little bit more effect. And we can add drug all day long, and once we get pretty close to maximal effect, we're not going to get any more effect by adding more drug. All right, so now this blue curve is our agonist dose response curve. To make things completely confusing with our natural curveball, let's throw some competitive antagonist into the solution and now look at the agonist dose response curve. So here the blue line is agonist dose response curve with agonist by itself. And here is the agonist dose response curve, but we've thrown some competitive antagonist in there to compete with the agonist. Well, notice that to get half of the maximal effect, we have to add much more drug in the presence of competitive antagonist. And notice we can continue adding agonist and continue adding agonist and win the competition and eventually get maximal effect, which is somewhere behind my head, which is fine. But here is the agonist dose response curve when we add non-competitive antagonist. Notice in the presence of non-competitive antagonist, the receptor is modulated in such a way that we never reach maximal effect no matter how much agonist we add. And this is why non-competitive antagonists are used in pharmacology so much, because notice the agonist does not win the competition and eventually reach maximal effect as it did with this curve. Notice with competitive antagonists, we can add agonist and eventually get maximal effect. So here's the agonist dose response curve in the presence of non-competitive antagonist. And notice that our maximal effect is brought down to here when we have non-competitive antagonist. And what I wanted to show you is this, that when agonist, on an agonist dose response curve in the presence of non-competitive antagonist, the EC50, the dose to get half of maximal effect, is the same dose. For what? For those of you keeping score. Well, then you change pages in Katzong, and all of a sudden the curves look completely different. And so when you read different pharmacology books, all those agonist dose response curves are all going to look different because of this concept called a logarithm. And so instead of that bottom axis on our curve being linear, we can make them logarithmic, and that's abbreviated log. And so here is a linear curve, or a linear axis. And so that means each little hash mark is equal to the other hash mark. I think I took some slides without taking them out of your notes. And so here is a linear axis right here. Note 1, 2, 3, 4, 5. Each space between the hash marks is exactly the same. But notice what happens when we make it logarithmic. It's the same thing if we use a log base 10. 10 to the 0 is equal to 1. 10 to the first is 100. 10 to the first is 10. 10 to the second is 100. 10 to the third is 1,000. 10,000, 100,000, a million, and so forth. And so notice each hash mark is 10 times more than the previous hash mark. That is the definition of a logarithmic scale. So when you read pharmacology books, whichever one you're reading during sunny days at the beach, be on the lookout for whether the axis is linear or logarithmic or semi-logarithmic. You can make the curves look like anything you want to. You can make curvy things straight by converting to some form of logarithmic scale. And logarithmic scale just essentially means that each hash mark is 10 times the previous one if you're using a log of 10. So you might see an agonist dose-response curve that looks like that, and notice our agonist concentration in this case is linear. But if we make it a logarithmic dose-response curve, notice it has this pretty S shape. And so this is a logarithmic dose-response curve. And so that's why the dose-response curve will look like this in one book and look like that in another. What I did want you to see about that was not that pop-up there, but this right here. Notice little teeny tiny concentrations, only teeny tiny concentrations of drug. Small changes in concentration is all that's required to make big changes in effect. And so notice how much leverage or how much control a drug has over the receptor. Only small increases in drug can make big changes on the receptor. And this is one of the natural properties of natural biologic systems. So everywhere you look, you'll see natural curves. For those of you who love mathematics, if you want to see the natural world in action, sit down and do the proof for the natural logarithm. But you do not have to do calculus to know natural curves, I assure you. But where these curves come from is all the same place. And the only reason that we suffered through any of that is to define these things right here, potency versus efficacy. Now, something important to know, when I went to medical school, they taught me this exactly backwards. And that's not really what's important. The importance is that you at least have these terms bounce around in your head for a few years before you get out into the clinical setting. I'm here to tell you that you have the rest of your life to learn pharmacology, and I can encourage you to do that. My first pharmacology class was about 20 years ago, I think, even more, unfortunately. My first pharmacology class was a long time. It's taken me 20 years to figure all of this out. And so it's going to take you a little bit longer than the few weeks that we have. But I do want you to know the difference between potency and efficacy, because I saw this on a board review book and thought, well, nobody has any idea what that means. So efficacy, fortunately, refers to the effect of a drug. The more the effect of a drug, the more efficacious the drug. So here is what I saw in the board book, and it didn't even say it was a logarithmic dose-response curve. They just threw these two little S shapes in there and wanted to know which drug had more efficacy. Well, the yellow drug has more efficacy than the blue drug. Notice the blue drug has less maximal effect than the yellow drug. So let's take morphine and Tylenol, which are both analgesics. Morphine is a opiate analgesic, which has much more maximal effect than Tylenol. And so notice that we see that by having much more effect on this part of the axis. Despite what the manufacturers of Tylenol will tell you, Tylenol does not have anywhere near the efficacy that morphine does, and so its dose-response curve would look like this, because this would be the maximal effect of Tylenol. The effect of the drug can be anything you imagine, and so we can think of this as pain control. Tylenol will give us this amount of pain control, but morphine will give us this amount of pain control up here, because morphine has much more efficacy than Tylenol. But potency refers to the concentration of a drug needed for that effect. So that means less concentration is required. So the less concentration of the drug required, the more potent the drug is. And so notice this drug achieves maximal effect at lesser concentration than the green drug. If I look at this right here, notice that if I add about this much drug right here, I get this much effect from the green drug, but the same amount of drug would give me all this effect over here. So we'll take Dilaudid, which is an opiate analgesic, a synthetic one. It has much more potency than morphine because we can achieve maximal effect with Dilaudid at a much smaller dose. A milligram of Dilaudid is a lot of pain relief. A milligram of morphine is not. And so Dilaudid has more potency because we get more effect at that dose than we do the other drug. I saw this in a board book, a nursing board book of all things, asking which one of these two curves had more potency and which one of these two curves had more efficacy. So I want you to take a very careful look at those curves and see if you can shake the dust off of that knowledge when that time comes. But notice these two drugs have the same efficacy. Different in potencies, but same efficacy. Yes, we see nodding in the classroom. That's a good sign. Notice again, these terms are commonly used interchangeably. They taught it to me in medical school backwards. I've listened to countless drug reps use these terms in reverse, but you will need to know the difference in this class. There's this thing called a quantal dose effect curve. Katzung has a very long and complicated description of quantal dose effect curves. So those of you going to be rocket scientists or professional pharmacologists, you'll want to take a very careful look at that. But I'm going to give you a simple explanation for quantal dose effect curves. With a quantal dose effect curve, the effect is either achieved or not achieved. Quantal just means there is a specific difference between one state and another. There's not this continuum of it. And so it's kind of like a light switch. The light switch is either on or off, which is different than a dimmer switch that has this complete continuum between on and off. And so quantal dose effect curve is just like a light switch, either on or off. So we'll talk about drugs to stop a seizure. And the effect that we want from the drug is to stop the seizure. There is no in between. The seizure is either ongoing or the seizure stops. And so a drug that is used to stop a seizure, we could describe that as a quantal dose effect curve. And so either there's going to be no effect or the seizure is going to stop, meaning the drug has given us maximal effect. Or like drugs to stop ventricular fibrillation, which is cardiac arrest. Ventricular fibrillation, we'll talk plenty about that, abbreviated VF or VFib. As we add drug to stop VFib, it doesn't lessen the VFib and lessen the VFib. They either have VFib or the VFib has converted into another rhythm. There is no in between. So when we give a drug, we're either going to get no effect, meaning they're still in ventricular fibrillation, or we will get maximal effect, meaning we have converted the rhythm into another one. And so you'll see quantal dose effect curves look like this. As we add drug, we get zero effect. We add drug, we have zero effect. We add drug, we have zero effect. We add drug, we have zero effect. We get to a point where we have maximal effect from there on after. Well, I don't think there's too much after this.
This is Cable 55, UH Maui College Television Network.